Again, the purpose of this video is to work demo number 1, lesson number 5. It should be a pretty quick one. There's a couple of very easy questions here, so let's do it. All right, so question number 1, we get into calculating a test statistic, and it's really important. No, we don't. We get into calculating a p-value. The directions, which it would kind of be nice if I read, is calculate a p-value for a two-tail hypothesis test, which means we just have to multiply by 2. More about that in just a second. For a z-stat, so it tells me I have to use the normal calculator, not the t-calculator, for negative 1.73. So this is the way that plays out. So go to the calculator, go to normal, and since we have z, we know that we use the standard normal distribution, mean 0, standard deviation 1. And we have a negative number, so for the test statistics, so that means we have to find the area in the left tail. If the z statistic was positive, we'd have to find the area in the right tail. So I need less than, and I need less than negative 1.73. And I calculate this, and you say, well, that's not the answer you gave. No, because we have to multiply by 2. When we have a two-tailed test, we have a p-value in the lower as well as the same area in the upper. So we have to multiply by 2, so 0.0418 times 2 is 0.0836. Now, another way to do this, I don't know, this may work for some of you. If I go negative 1.73 and 1.73 using the between option, notice I get 0.9163. So I'm getting the area in the middle, but I don't need that area. I need this area down here, and I need the area up here that's in the white. Well, if I take 1 and subtract 0.9163, well, I get 0.0836. So just another way that you could have worked this problem. All right. Next question. Magazine reported that the top 50 business schools studied an average of 12.4 set up hypothesis test to prove that the mean number of hours studied, to try to prove, is different than 12.4. So I selected J because it's the only one that makes sense. First of all, we know that the null hypothesis has to be mu, when we're testing a mean, has to be mu equal. So I can get rid of A because that's mu not equal. I can get rid of B, that's alpha, that doesn't work. I can get rid of C, X bar. We don't need to make any hypothesis test about X bar. We know X bar. X bar in this, well, this is a type 1, so X bar would just be the sample. Alpha doesn't work, beta doesn't work, X bar doesn't work, beta doesn't work, alpha doesn't work. Okay, mu equal 12.4, but then the alternative hypothesis also has to be mu. So the X bar, so that's the reason I doesn't work. K doesn't work because we can't have not equal to in the null hypothesis. It always must be equal to. Obviously, L doesn't work either. Now, a type 1 error for part B, this is where the null hypothesis is true, but we reject it. So the only one that aligns with that would be concluding that the mean number of hours studied is different, because we would have rejected the null in favor of the alternative, which is not equal to, when in fact it is not different, when in fact it is 12.4. So it's the only one of the 3 choices we had that made sense with the definition, to align with the definition of a type 1 error. Now, a type 2 error is where we fail to reject a false null. Well, the only selection there is B, which says concluding that the mean number of hours studied at your school is not different when it actually is different. Again, that aligns with a type 2 error, which is failing to reject a false null. I'll tell you, type 1 and type 2 errors can be a little bit confusing, even as much as, for the last, I got my PhD in 2002. So I probably started it in, 1997 or so. So anyway, I'm posting these videos in 2022. So for the last 25 years, I'd say there have been very, very few days I haven't studied statistics. For me, even with my experience, I have to go back to the definition, to that table that I presented in the previous videos to work those types of problems. All right, calculate the degrees of freedom. Well, it doesn't get much easier than this. The degrees of freedom is just n minus 1. So 16 minus 1 is 15. All right, so we're going to get into critical values. Now, what we get here is we get into a situation where the sample standard deviation is given, but the population standard deviation is not given. When we have a problem like that, we have to go to t-stat. But I want to do a calculator, so I want to do the t-calculator. So the first thing it's going to ask me to enter there is going to be the degrees of freedom. So I go directly to n, which is 25, subtract 1. Now the next thing I need are the critical values. So I'm going to work on this negative one first. So my alpha value is 0.05. So in the left tail, I need half of my significance level. So I need 0.05 divided by 2. Now I can hit compute and it will find the critical value for me, negative 2.0639. If I want the upper tail, I can do a couple of things. First of all, I can say because of symmetry, it just has to be the positive of the negative 2.0639. Or if I want to kind of prove that to myself, I can just go 0.05 divided by 2, put it in the upper tail because I've selected greater than, and I get 2.0639. So just enter those two numbers separated by a comma, and you got it. Now, the next thing we get into is we get into a test statistic. And there are 3 different types of test statistics. There's a T statistic when we're calculating or conducting a tested hypothesis for a population mean, when the population standard deviation isn't given. And again, I'm not going to go into this a lot because this has been taught in previous videos. I have when a Z statistic, test statistic, when the population standard deviation is given. If it's not given, you use the sample. I have to use a different distribution. And then I have the situation where I have proportions. But what I have in this case is I have a test statistic T as denoted by the T right here, then STAT. So I need to put in the sample mean, which is 56. I need to put in the hypothesized value for mu, which is 50. Need to put in the sample standard deviation, which is 15. And I need to put in the n, which is 25. Now on top, I get 6. The bottom, I can do a little mental arithmetic. 15 divided by 5 is just 3, equal to. Now, it doesn't always happen where these work out nicely because you could have maybe 15 divided by the square root of 47, which, I can't do that. I have to use a calculator. So if you're going to use a calculator there, let me pop this in the calculator real quick and show you something that's very critical. All right. So what you'll notice there is, let me put some light. What you'll notice there is that when I entered the numerator, 56 minus 50, put that in parentheses. And when I entered the denominator, 15 divided by the square root of 25, I put that all in parentheses, so I get correct order of operations. So that's something that I've seen students do a lot. They kind of know the correct formula to use. They just don't enter it in their calculator correctly. Now, state your statistical decision. In a previous video, I said that if our test statistic is between the two critical values, then we fail to reject. We do not reject. So this tells us the data does not provide sufficient evidence to conclude that the mean differs from mu equal 50. Again, in this test, go back up to the top. The null hypothesis is mu equal 50. We don't reject that. Therefore, we can't conclude that the mean is different. In a sample 117 from a right-skewed population, would you use a t-test? Well, the key there is, does the central limit theorem kick in? Because we need a sample size of 30 or bigger, 30 or larger. And in this case, we have 117. So yes, I would use a t-test because the sample size is at least 30 and the central limit theorem kicks in. All right, so a manufacturer of chocolate candies, just pause the video and read that. So there's a claim that, so the packages are labeled 8 ounces, and the company wants the packages to contain 8.17 ounces, so they're going to give the customer a little bit more than what they think they're getting. So sample, so if the process, there's evidence the mean amount packaged is different from 8.17. So my null is mu equal 8.17, and it's not equal to 8.17 because of the intent of the study. The critical values are, so what do we have here? We have a sample of 50. And in the left tail, we are working with a significance level of 0.10. So the left tail is negative 1 point, or the left critical value is negative 1.6766. Again, right here where I'm circling is the significance level I used. And then you just always know you put the positive there. What is the test statistic? I would take a different approach here. Let me explain to you what I would do. Instead of working the test statistic formula that I gave you a while ago, we have enough information here to actually run the test. So I can go T, one sample with summary, because I don't have my data. I have my mean and my standard deviation, my sample size. So I'm going to run that. So the sample mean looks like it was 8.171, given in the last sentence. Well, next to last sentence. Sample standard deviation is 0.058. And the sample size was 50, right? Yeah. So I want to test 8.17 against not equal to 8.17. Now here's the key. You can actually get your critical values right there. We have to change this to 0.10 because we're testing at a different significance level than 0.05. And I can hit compute. Now, the test statistic is 0.1219, which I get right here. And you can see that the critical value is right there. So I could have got that a different way. So I'm going to use the p-value approach. So my p-value is 0.9035, so I'm not going to reject the null, so I do not reject H sub O. There's insufficient evidence to conclude the population mean amount differs from 8.17. Calculate the p-value. Well, there it is, 0.9034. I got that from the output. And the only interpretation that makes sense is this one right here. So the p-value is the probability of attaining our sample mean or something more extreme if the null hypothesis is true. So that's the key part of that, the interpretation, if the null hypothesis is true. So the interpretation of the p-value will always be in the context of if the null is true, then what's the probability of obtaining our sample mean or a sample mean that's more extreme. All right, we're done. I thought there was another question. All right, take care. Hope this helped.